আচ্ছা, শোনা যাচ্ছে তো?
হ্যাঁ
জাস্ট 1 minute. Some examples. Number one, stars. A subset x of a norm linear vector space, linear space E is called a star with vertex T if for all x belongs to x 1 minus t x plus tp belongs to x for all t belongs to I. Okay, define.
আপনি কন্ট্রাক্টিবল স্পেসের এক্সাম্পল করছেন তো? ঠিক আছে।
Define h x cross I x cross I to x xt goes to 1 minus x t plus tp, then h is continuous. Okay, h x 0, you can check it, h is continuous by sequential criteria. rdx x for all x belongs to x h x1 equals to theta px for all x belongs to x, where theta p x to x goes to p. Okay, is the map. So h is the homotopy, identity x theta p. Therefore stars are contractible.
দাদা রেকর্ড করতে দিয়েছো তো?
হ্যাঁ, stars are contractible. Okay, number 2, same type example, convex set. A subset x e of a norm linear space E is said to be convex if xy belongs to x implies 1 minus tx plus ty belongs to x for all t t belongs to I. Let p belongs to x and theta p x to x goes to p, then h x cross I to x xt goes to 1 minus t x plus tp. Define the homotopy between identity and theta p. Hence convex sets are contractible. Actually, any convex set is a star, hence contractible. Example 3 or observation. Like to say observation. Page number 2. For each lambda belongs to L, let x lambda and y lambda be spaces with same homotopy type. Prove that x equals to product x lambda belongs to L, same homotopy type to y, which is product of I want to write this product of y lambda belongs to L equals to y. Okay, the proof is very simple. Proof. Suppose f lambda x lambda to y lambda be a homotopy equivalence for each lambda belongs to L. Define f product of x lambda belongs to L to product of y lambda belongs to L x lambda f lambda x lambda L. Note that F is continuous as each if lambda is continuous. Suppose g lambda y lambda 2 x lambda be the homotopy inverse of f lambda, then define g product of y lambda product of x lambda y lambda lambda belongs to L goes to g lambda y lambda L. Then g is continuous as each lambda is continuous. Let lambda homotopic to identity y lambda and p lambda homotopic to identity x lambda for all lambda belongs to L. So H lambda is y lambda cross I to y lambda cross I to y lambda and x lambda I to x lambda with some property. Define H product of y lambda belongs to L cross I to product y lambda small y lambda belongs to L comma T goes to just 1 minute. Goes to H lambda y lambda T such that lambda belongs to L. Then H is continuous as each what is this? B homotopy. I wrote it by notation, okay, or continuous. So as each H lambda is continuous And what P? Product of x lambda, lambda belongs to L, cross I to product of x lambda, lambda belongs to L, such that x lambda t goes to p lambda x lambda t, lambda belongs to L. Then H F compose G homotopic to identity Y, and P G compose F homotopic to identity X. This is your check. Corollary for the corollary of this observation: if the space X is contractible, then for every space Y, X cross Y is homotopic type to Y. Okay. Proof: as X homotopic type to X0, therefore X cross Y homotopic type to zero cross Y as X0 cross Y is homeomorphic to Y. Homeomorphic to Y. Okay. Comb space. The comb space Y is defined as Y xy belongs to R square 0 less or equals to 1, x equals to 0, 1 by n, or 0, 1 with subspace topology. Exercise: show that comb space is path connected. Comb maximum space is path connected and contractible. So if you show it is path connected, then next you have to show it is contractible. So both are very easy. So it look like very look like this. Okay, so you project it, then it is a equivalence. Y is homotopy type 2, Y is homotopy type 2 I. If we project via this is your homotopy equivalence, pi y to I, x y goes to x is a homotopy equivalence. Now I is contractible. This implies Y is contractible, and hence it is path connected. Okay. Number 3. Definition, which some definitions. A subspace A of X is called a retract of X if the inclusion map A to X has a left inverse in the category of topological spaces. And continuous map. Hence A is retract of X if and only if there is a continuous map R X to A such that R compose I equals to identity A, that is Rx equals to X for all X belongs to A. Such map R is called a retraction of X to A. A subspace A of X is called a weak retract of X if the inclusion map I A to X has a left homotopy inverse that is left inverse in the homotopy category. Thus, a weak retract A is a weak retract X if and only if there is a continuous map R X to A such that R compose I is homotopic to identity A. Such a map R is called a weak retraction of X to A. Okay. Note that every retraction R X to A is surjective. Because in A it is identity and satisfy the commutative diagram that means R is an extension of identity to X. A equals to A belongs to X such that RA equals to A. Hence, if X is Hausdorff, A is a closed subset of X. Because in Hausdorff space singleton set is closed. Closed subset of X.
Excuse me, I was just talking that I was just saying that it may happen that I mean the inverse image of, I mean minus a, I mean uh, I'm trying to say,
Obviously,
I mean the set should contain a, but can it, is it exactly a?
hmm?
I mean RA equals to a for all a belongs to a, that's fine. But it might happen that X has a bigger subset, say B, which contains A, and I mean R is R restricted to R.
Codomain is A, right?
Huh.
Then repeat your argument.
Sorry?
Codomain is A. Codomain of R is A, capital A. Then repeat your
Oh,
argument.
no. Sorry.
Okay. Example. Let sorry small x belongs to x, then is the retract. This is trivial example because there is a constant map. What is the retraction? Identity inclusion theta x. Right, a goes to x. Okay. Next, this is trivial example. Let A be a discrete space with more than one point. Then A is never a weak retract of a connected space. A weak retract connected space X with X. Since X is connected, any continuous map fx to a is constant since a is discrete. That means A is a space with discrete topology. But A is discrete with more than one point, so hence there exists no map x to a such that the diagram is commutative. Because R should be constant then. Okay. Number 4. If A is a retract of X, then it is a weak tract of X, but converse is not true. Let I subset of I square subset of R square, where I equals to obviously 0 1, and A subset of I square not A, I want to say Y subset of I square be the comb space, then A and X, not A, Y and X, oh, I should write A because A is my example. A be the cone space, then A and X both are contractible. It is your homework that comb space is contractible. Hence, A same homotopy type to X, and you can see that A inclusion map is a homotopy equivalence. But comb space is not retract of I2.
Are we going to use the logic that it is not locally path connected?
Yes. Then this statement will prove by Ovidup. I will leave it.
Okay, just then we can just mention it as a homework. Then then we will just fill it up.
Suppose R I squared to Y be a retraction. This is a problem of HR also. where oh, not y, this is my a. I have written here cone space by y, that's why I am writing y. Where a equals to, recall what is your cone space, x y belongs to r square such that 0 less or equals to y less or equals to 1, x equals to 0 1 by n, or y equals to 0 0 less or equals to x less or equals to 1. The comb space with subspace topology as 0 1 belongs to y. This implies r01 equals to 0 1. Let u01 be any open set containing in A then R inverse u01 is an open set of I square. Therefore, there exists epsilon greater than 0 by Archimedean property such that B epsilon radius 0 1, I don't know, it is enough, right? Intersection I square, enough to understand that epsilon radius and 0 1 center, subset of R inverse u01 since limit n tends to infinity 1 by n 1 equals to 0 1, or you can use Archimedean property. This implies 1 by n 1 belongs to B epsilon 0 1 intersection I square for all n greater equals to m for some m belongs to m. Okay, so this now B epsilon 0 1 intersection I square is path connected, is convex. Actually, this implies 1 minus t 0 1 plus t 1 by n 1 belongs to what is this, equals to t by n comma 1 belongs to B epsilon 0 1 intersection I square, that is subset of R inverse u 0 1, okay, for all t belongs to I. Hence R t by n 1 belongs to u 0 1 for all t belongs to I. Let alpha I to a t goes to R t by n 1, then alpha is continuous because it is straight line and composition by R and it is this guaranteed that RT by N1 belongs to U01. Hence alpha is a path joining 01 and 1 by N1, as R 1 by N1 equals to 1 by N1, because 1 by N1 belongs to C. C not A. 1 by N1 belongs to A. Okay. So now I leave it to exercise. Overlook that he says that it is not locally path connected, so it is our point, and B epsilon 01 intersection I square is some now this is your strips. These are your strips like this. So now in locally what it's look like, if I magnify this, it look like some strips after 1 by n it will lie here. So there is no path between 1 by n. Suppose this is your 1 by n comma 1 and this is your 0 1, so there is no path, so arrive a contradiction. Okay, now complete it, and it is not locally path connected. কি এটা কমপ্লিট হবে?
Yes, I mean, that is, I mean, it is enough. I mean.
Okay. 5. Definition. Let XA be a topological pair and Y be a topological space. XA is said to have the homotopy extension property with respect to Y if given maps G x to Y and capital G A cross I to Y such that small gx equals to capital G x0 for all x is to A, there is a map f x cross I to Y such that if 0 equals to gx for all x is to x, and f restriction a cross I equals to G. If G is regarded as a map of, you know that X is homeomorphic to X cross some point, so I can Gx to Y, I can write same G, I can think this is regarded a map G x cross 0 to Y. The existence of F is equivalent to the existence of a map represented by the dotted arrow which makes the following diagram commutative. So what is diagram? So diagram is like you have A cross 0, then it is sitting inside A cross I, and it is sitting inside also X cross 0, and it is sitting inside X cross I, and this is sitting inside, this is your, now it is your Y, homotopy extension with respect to Y. Now this map is given small g is X to Y map, so I can think it is X cross 0 to Y map. Okay, and given capital G also here, such that at the 0 level it is same restriction, so G restriction A cross 0 is same as G restriction A cross 0, they're same. So there exists here to here a map F such that F restriction A cross I is G, and obviously F restriction X cross 0 both respect. Okay, so this is called homotopy extension property with respect to Y. The topological pair X comma A is has a homotopic extension property with respect to Y. Observation: notice that if XA has the homotopic extension property HEP, extension property with respect to Y, and F0, F1, A to Y are homotopic, then F0 homotopy if f0 has an extension 2x, then f1 also has extension 2x. Okay, so if they are homotopic and one of them has extension can be extend to x, sorry, one of them map can be extend to x, then f1 also extend to x. Proof. Suppose g x2y is an extension of f0, that is gx f0x for all x belongs to a. Let a cross I to y be a homotopy between f1, since x a has the homotopy extension property, there exists f x cross I to y such that f restriction a cross I equals to g and f x0 equals to gx for all x x. If a belongs to a, then a1 equals to 1 equals to f1a. Hence f restriction x cross 1 is an extension of f1. So you see in the proof, not f0 f1, you can take arbitrary ft, t belongs to I, then if f0 has an extension to x, then ft also has an extension to x. Okay, you restrict x cross t. It follows that whether or not a map a to y can be extended over over X is a property of homotopy class of the map. Of the homotopy class of the map. Okay. Next, just one definition, then I will stop for today. Okay. 6. Just one definition, then definition. A map, if x prime to x is called a cofibration if for any space y and given maps g x to y and g capital G x prime cross I to y such that f x 0 equals to gx such that g f x prime g x prime 0 for all x prime there is a map if x cross I to y such that if x0 gx for all x and if x prime t for all x prime belongs to x prime and for all t belongs to I. If G is regarded as a map x cross 0, then we have the following diagram. So by the diagram you can understand what is happening here. You can understand easily what is happening here. So I should write black x cross 0 sitting inside x prime cross I. Now in the homotopy extension property there is inclusion, but there is a map here via f, right? Now here is also map via f, Now rest of them are same. I don't write it as by inclusion. I just write by normal map. This is not inclusion, so it is a more general property. Not This is not inclusion. There is a problem. Now rest of them are same. So there is y, and hom- homotopy extension, one more mention that homotopy extension property with respect to some y, and cofibration is for any y. So that is your f. So
Can we go back a little further? মানে একটু উপর দিকে দেখা যাবে?
hmm,
হ্যাঁ, okay. Just a second.
now you can take x prime as a subspace of x and inclusion map instead of f. Then inclusion map is a cofibration if and only if it is x comma a, the pair x comma a has homotopy extension property for any space with respect to any space y, right? Note that an inclusion map x is a cofibration if and only if, this is just language, nothing to prove here, xa has the homotopy extension property HEP. With to any space y. So now your homework is find a cofibration map, cofibration pair, or find an example of this. Okay, any question? Find an example.
Yes, just a moment. I'm trying to, not an example, but I'm just trying to, just a moment.
I'll give some example later, but try in the meantime you will find it an example.
Why the name cofibration?
এই সব প্রশ্ন জিজ্ঞেস করলে আমি জানি না।
I mean, is it some sort of a fiber product, or I mean something like that? Co-fiber product.
ও পরে দেখবো।
Oh.
ভদ্রসভ্য প্রশ্ন করবো, এই নাম করে অন্যের স্বার্থকতা একটু পরে বুঝবো।
Just
রেকর্ডিংটা অন আছে।
No, it's fine. I mean, I was trying to see, I mean, if say for any map, I was trying to come up with something like from a cofibration, can we imply that, say if there is a cofibration from a set to this set, then something from homotopy extension property, does it follow? Not exactly the latter version that we have mentioned. I mean, okay,
क्वेश्चनটাই
I will
বুঝলাম না।
try. Oh, okay, I will try later and then try to formulate it properly.